Now let's show the fourth part, which was that closed sets are Lebesgue measurable. And to prove this result, so this fourth part is requires some more careful attention than the other parts, and so we will need two results to prove this fourth part. So first is a theorem which says that every open subset of RD is a countable union of almost disjoint boxes. In fact, almost disjoint closed cubes. So I will not prove this theorem, and I'll just refer you to see the proof in Terence Tao's book. And this is, it's given in lemma 1.2.11. so the proof is quite detailed there and not very hard to follow, so I'll leave the proof for you to learn and understand. Of course, if you have any questions, you can ask on the portal and we will be happy to answer. So this is the first result that we will need, that every open subset of RD can be written as an countable union of almost disjoint boxes. The second theorem that we need, or rather this is a lemma, is that this is a topological fact that if E and F are disjoint subsets of RD such that both are closed and at least one is compact, then the distance between E and F is greater than 0, which is to say that E and F are separated. So I will again leave this as an exercise. This is an exercise in topology. Which uses the concept of compactness, and so we will use these two results to prove that closed sets are measurable. So let's see how this is done. So first, we can suppose without loss of generality, that if E is a closed set, it is bounded also. It is also bounded, because if not, then E can be written as the union n equal to 1 to infinity E intersections with, let's say, the ball with center 0 and radius n. So now this is a closed and bounded set, and so if we prove that closed and bounded sets are Lebesgue measurable, then E will be a countable union of closed and bounded sets, which are, each of them are Lebesgue measurable. So therefore this will imply that, so if we prove that closed and bounded sets are Lebesgue measurable, then this will imply that any closed set is in fact Lebesgue measurable. Because we can write it as a countable union of closed and bounded sets. So we can suppose without loss of generality that E is a closed set which is also bounded. So now we can use the, now given epsilon greater than 0 and using the fact that M star E is finite, because now it's closed and bounded also, so the Lebesgue outer measure is going to be finite. Choose an open set U containing E such that we have M star U is less than or equal to M star E plus epsilon. So we have to show that M star of U minus E is less than or equal to epsilon. So note that U minus E is an open set, so this implies that U minus E can be written as a countable union of almost disjoint boxes. So BI is a countable union of almost disjoint closed boxes or cubes. This is from the theorem that we stated above, and so we get that M star U minus E is the sum of all these almost disjoint closed boxes 1 to infinity. Now if we can prove, we can show that this sum I equal to 1 to n MBI is less than or equal to epsilon for any n greater than or equal to 1, then we are done. Because what we have then is that M star U minus E is equal to the limit of n tends to infinity I equal to 1 to n M of BI, and since each of them is less than or equal to epsilon, the limit is also less than or equal to epsilon. So we have to show that any finite sum I equal to 1 to capital N MBI is less than or equal to epsilon. Now take, for this purpose, we can take E union of these n closed boxes. So here E is closed and bounded, and these are also closed and bounded. So this implies, and also that this is a disjoint union. So this implies that M star of the union of these two things is equal to M star E plus M star union I equal to 1 to n BI, because of finite additivity for the separated sets E and F, which is the finite union of BIs, and here we are using the lemma stated above. So M star E union, this finite union of BIs, is equal to M star E plus M star of this union of BIs from I from 1 to n. But M star of E union 1 to n BIs, this is less than or equal to M star of U, because this set is a subset, since E union BI is a subset of this set U, because this is a subset of U and this is a subset of U minus E. So the union is still a subset of U. So by monotonicity we get this inequality, and on the left hand side we have M star E plus sum of MBIs I from 1 to n, and on the right side we get M star U, but remember that U was chosen so that it was less than or equal to M star E plus epsilon. So this implies that I equal to 1 to n MBI is less than or equal to epsilon, says since M star of E is finite. So we can cancel out these M star E and this M star E, and so we got what we needed, which is that this sum I equal to 1 to n MBI is less than or equal to epsilon for any n. So this proves the result. So we have proved that closed sets are also Lebesgue measurable. Now let's come to the complement. I think this was part 5. So let E be Lebesgue measurable, and we have to show that E complement is Lebesgue measurable. So we proceed as follows. For each natural number n greater than or equal to 1, choose an open set UN containing E. This is a Lebesgue measurable set. So we can choose UN such that M star of UN minus E is less than or equal to 1 by n. So here we are taking epsilon to be 1 by n, and for each n we are choosing an open set UN such that this inequality is satisfied. And now put Fn equals UN complement. So we would like to take, so this is a closed set. Fn is closed for each n greater than or equal to 1, and now we put F equals the union of all these Fn's from n equal to 1 to infinity. So we will show that M star of E complement minus F equals 0, which would imply that E complement, which is the union of F and E complement minus F, and now if this measure is outer measure of E complement minus F is 0, then this is Lebesgue measurable, and F being a countable union of closed sets, this is Lebesgue measurable. So the union is E complement is Lebesgue measurable. So we have to show that M star of E complement minus F is equal to 0. So how do we show this? So note that M star of E complement minus F is equal to M star E complement minus the union n equal to 1 to infinity. This is the by definition of F here, and so this is M star E complement intersection with the intersection of the complements of Fn. So each Fn complement is Un by definition. So this is less than or equal to M star Un intersection E complement for all n greater than or equal to 1, because this is contained in Un for each n, and we have chosen this such that this is 1 over n is less than or equal to 1 over n. So this is true for all n, therefore this goes to 0 as n tends to infinity. So therefore this M star of E complement minus F is 0, and we are done. So if E is Lebesgue measurable, then E complement is also Lebesgue measurable. Finally, we come to the last part, which is the 7th part, which says that if En 1 to infinity is a collection of Lebesgue measurable sets, then the intersection n equal to 1 to infinity En is Lebesgue measurable. So this is quite easy. So one can write intersection of these Ens as the union n equal to 1 to infinity En complement. So this is by De Morgan's laws. So since each En is Lebesgue measurable, this En complement is Lebesgue measurable, so the countable union of Lebesgue measurable sets of En complement are Lebesgue measurable, and finally you take the complement, which is again Lebesgue measurable. So this is just a one line proof that countable intersections are also Lebesgue measurable.